Here's a problem where we want to find the area enclosed between the graphs of two functions, but this time the curves intersect enough times that there's two regions and formed by three intersection points. We weren't given all of the required information in the problem. We were really just given the two functions. I went ahead and put the graph over here on the right, and I've already gone ahead and I've solved an equation to find where the three intersection points were, just in case we didn't see it in the graph clearly enough. So I made f of x equal to g of x. I set 3x cubed minus x squared minus 10x equal to negative x squared plus 2x. I have brought all the terms to one side, so I have 0 on the other side. And we have a polynomial now that we can go ahead and try and factor. And I've gone ahead and factored out the common factor of 3x, leaving x squared minus 4. And notice we can factor that down one more time. X squared minus 4 factors down to x minus 2, x plus 2. And now taking each factor equal to 0, 3x equals 0 means x equals 0. And likewise, x would equal 2 and x would equal minus 2. Now I look at my graph and I can see those 3 points, those 3 values of x are the important points. Here in the very middle, we can see the two curves intersecting at x equals 0 at the origin. We can see them intersecting also here when x equals negative 2, down here at the point negative 2, negative 8. And I see them intersecting again over here at the point 2, 0. Now notice though, in the first region that I've kind of designated area 1, in that section between x equals negative 2 and 0, the graph that is above the region is the graph of f of x, the cubic function, which kind of continues on and follows around into over here. And then the lower function is the quadratic function g, which is this parabola right here. I'm tracing it out right here. Okay, so in area 1, f of x is the upper boundary and g of x is the lower boundary. And so what's going to have to happen here is we're going to have to write two separate integrals to combine the two areas, because one function is not the upper function the entire time, right? So what's going to have to happen here is we're going to have to find area 1 and add to that area 2. In this video, we're only going to show the setting up of the two integrals, and then presumably solving the two areas would be something you could do after that. So primarily here, area 1 will be the integral where f of x is the upper function and g of x is the lower function. And this interval starts at the x value negative 2 and goes to 0. And when I go to area 2, now g of x is the upper boundary and f of x is the lower boundary. So for this interval, which starts at 0 and ends at positive 2, g of x needs to be the upper boundary and f of x needs to be the lower boundary. So this shows up the setup that's required. You certainly cannot assume, that the two areas are the same. They don't have the same shape. There doesn't seem to be any symmetry here. And so we would have to solve for the area 1, which I'm just going to make a note of there. We need to find the value of this one. And then we will find the area 2 with this type of integral. And then at the end, we add them together to get a grand total. Because you have it set up the right way, where f of the upper function is listed first, in each one, these should both give positive answers. And then we have the two positive areas to add together at the end. Okay, so the purpose of the video here is just to kind of point out the general idea. The intersection points are required to be found, and we find them first, generating the two regions, and then we set up a separate integral for each region, and then we wind up at the grand total at the end. I'm going to leave it to you to compute this if you want to go find the exact answer. This other problem, we're going to actually show two different ways to solve it, mainly because the way the problem is presented is a little different. The equations for the curves are shown where f and g are functions of y, not functions of x. So whenever that's the case, one way to think of this is that if I see f of y equals 3 minus y squared, it's similar. You can think of it similarly as like when you're given f of x, it's a synonym for y equals. So this is a synonym for x equals 3 minus y squared. And likewise, this is a synonym for x equals y plus 1. Now, we're used to derivatives and integrals and functions, everything in terms of x, where y is a function of x. In this one, f is given as a function of y, which means that y is the independent variable, x is the dependent variable. So for example, to plot this graph, we'd be picking values of y and solving for the x. For example, if I pick y to be 0, x equals 3, hence the point 3, 0. If y equals 1, x would be 3 minus 1 squared, or 2, so hence the point 2, 1, and so on. And if I were to pick the y value negative 1, I would also get x equals 3 minus 1, or 2, so hence the point 2, negative 1. So anyway, this graph is produced, the function f is producing this, what is really a sideways turned parabola here. Okay, so if you think about it, if it were y equals 3 minus x squared, you'd expect the parabola to start at 0, 3 and open down toward the negative side of the y-axis. So this is doing the similar idea, starting at 3 on the x-axis and opening to the negative side of the x-axis, doing the exact same thing. This one is easier to read. I could write it x equals y plus 1, which is how it's written, but if you want to draw it and see it more familiar, in a more familiar way, it also could mean, by solving for y equals x minus 1, and that is something we recognize. It's the equation of the line where the y-intercept is minus 1 and the slope is 1. And so the region we're interested in is this one right over here, in between the parabola and the line. Now, in terms of integrals, normally we're interested in the two intersection points or more, and then we slide across, always measuring between the upper function and the lower function. Well, this time, that would mean that I have to have these solved for y and have the functions in terms of x. I don't have that right now, other than what I already did here. So I'm going to have to solve for the intersection points first. I've gone ahead and marked them, and I set f of y equal to g of y to algebraically solve. And I set 3 minus y squared equal to y plus 1. And getting all that on one side, it gives me y squared plus y minus 2 equals 0. And I got one I can easily factor down and get y equals negative 2 and y equals 1. So you notice here, the 2 points we have marked, one of them has a y coordinate negative 2. It's the point negative 1, negative 2. And this is the point where x is 2, but the y value is 1. So you notice kind of in the side work, what we actually solve for is the y coordinate. And then by plugging those y values into either of these equations, you can get the x coordinate, negative 1 and positive 2. So the way we're used to solving areas is to consider the upper function and the lower function. Now, this one gets a little tricky because starting at the point negative 1, negative 2, the blue line, which is g, is the upper curve, and the red is the lower curve. But it's not that way the entire way across. Notice that when we get to the x value 2, things change, and now it's like the upper curve is this part of the parabola and the lower is this part of the parabola, which means we have to break this up into two parts by solving for y in that function for f of y. Okay, so I'm going to go over here and take the equation for f of y, and now I'm going to try and treat it as if it's a function of x by solving for y, which would make y squared equal to 3 minus x. And now there's really two functions here, the positive square root and then the negative square root. And so the positive square root draws the upper half. So in this context here, I'm going to label them y equals the square root of 3 minus x, and the lower half y equals the negative square root of 3 minus x. And we'll need those now, and I'm going to label the line also in the same way as y equals x minus 1. And now let's write our integrals to solve for the area completely enclosed by the two graphs. So there's the one section here between the point of intersection and then the vertical line on x equals 2, and where the blue is the upper and the red is the lower, and then there's the region between the vertical line and the end here at 3, where the two square root functions are bounding it. Okay, so I'm going to label this integrals with respect to x. So the first part contains an interval starting at the x coordinate -1 and then ends when I get to this point this value x equals 2, and the line, which is y equals x minus 1, is the upper function, and the lower function is this part, which is the negative square root of 3 minus x. And in a minute, we'll rewrite this and simplify some double negative signs and things like that. But to that, we have to add the area that is between this vertical line and then the end of the parabola here. And the x coordinates of these two boundaries are x equals 2 and x equals 3. And in this section, the upper part is the positive square root of 3 minus x. And then the lower function is the negative square root. Okay, so to rewrite this with simplification, it's the integral -1 to 2, and then my integrand is going to be x minus 1, and then I'll combine this two negatives to make a plus, the square root of 3 minus x. And then I will combine with that the integral from 2 to 3, and I'll simplify the double negatives here. Notice now that's just two of the same thing, so I would really write this as 2 square root 3 minus x. And the purpose of the video here now is just to talk about the setting up of the integrals. You can still take the antiderivatives of these two expressions and plug in the numbers there to solve for the final answer. Okay, so the purpose of this demonstration is just to talk about the setting up of the integrals. But I'd like to take a look at this problem a second time and show you how we could solve the problem with a single integral. So let's go and let's switch screens here. I've got the same two functions, the same graph and everything, and I still know the two intersection points. So I'm going to go ahead and label them again. Okay, this is still intersecting at the point -1, -2, and this is still intersecting at the point 2, 1.
Mike Wallace, please on extension 2300.
However, this time I'm going to label these equations the way they originally were given. The pink graph is f of y is 3 minus y squared. And the blue line is g of y, which is y plus 1. I want you to imagine that instead of the problem set up with respect to x, where in that situation, you're really thinking of it, when you're doing integrals, you often think of rectangles that are being used, and in the integral with respect to x, you'd be stacking these rectangles this way, throughout this region. So then the height of the rectangle is the distance vertically between the curves, and then the width is the little delta x. And you'd be filling these in all through the region here. Okay? However, we ran into the problem that once I got to this point at x equals 2, the boundary changed. It went from being the blue to the red to being the red to the red. So I'd like to propose and talk about maybe thinking about this a little differently. What if we were to draw the rectangles horizontally, where the main measurement was the horizontal distance between the curves, and then the little width is the change in y. And notice if I do this up near the top, the right end of the rectangle is the pink or the red graph, and the left is the blue. And it does not matter where I draw them. Anywhere in this region, if I draw them that way, it's the same thing. The blue on the left, the red on the right, all the way to the bottom. So I would like to think about this. If you kind of envision that with respect to the x-axis, the red is the upper function. It's got the highest x value of the two graphs. And the blue, any point on the blue curve has the smaller x coordinate. Then what we can think of in terms of this area is we can write the integral with respect to y and integrate across the y-axis and do one integral where we use the y-coordinates of these points. The lowest y-coordinate is -2 and the upper y-coordinate is 1. And as I look at the region, I go up it here. The function whose x-coordinate is the biggest every time is the red one. And the function whose x-coordinate is the smallest every time is g. So we understand that this single integral will solve the same area that we did on the previous screen with two integrals. Notice that setup would be simpler then. So integral from -2 to 1, 3 minus y squared, minus the quantity y plus 1. And if I wanted to keep going, we would just clean this up by combining some like terms, like the two constants. So +3 here, and then minus +1 there is going to leave 2. And the integral from -2 to 1. Again, we're just going to show the setup of the integral here. So notice we're also not working with square roots, whereas in the previous method, we had all these square root functions that we had to then integrate. But in this setup, I don't have any of that. So we just have not only a single integral, but a much simpler one to solve. And if you took the time now, either by working them out by hand or by putting them in your calculator, you'll find that both setups, the one we have here and the one we have here with two integrals, the grand total should be the same. Obviously, we have the same region. Okay, so this is an integral with respect to y. I like this example because it shows that we can solve it either way. It's possible to set up an integral with respect to x, and it's also possible to set up an integral with respect to y. Each one, I mean, depending on the situation, each one has its uses, and if you're familiar with both methods, then sometimes you can pick the method that will be the simplest. Sometimes integrating with respect to y is the easiest setup. Sometimes integrating with respect to x is the easiest setup. It just depends. This one, I think clearly this setup with respect to y is the simpler one. Well, I hope you have a good day, guys. Be working on this assignment in my math lab, and we will see you back here on next time we're together.